I thought I might do a bit of a review, but I'm just going to say a few words of sort of overview in way of review right now, and I'm not going to do a review till tomorrow night. Why don't we start by picking a time for the review tomorrow night? You guys have a preference? I was going to say, you know, somewhat later after dinner, 8:39, and then go for an hour, hour and a half. Huh? 8 to 9:30. Maybe perhaps longer. So this is review. Tomorrow, 8 to 9:30 p.m. here. And of course, you've got recitations tomorrow. So, right, take advantage of that. I have office hours right after this. I have office hours tomorrow at 11. Okay. Oh, and since we're here, apologies it took so long. Here, finally, is the distribution from the last exam. Oh, those are my kids. For my research, I got to live in Italy for 6 months. It's fantastic. And that's several years ago. I got to shrink this a tad. Oh no, it doesn't shrink. Okay, so darn it. Okay, well we'll live with it. I think you can see, right? So on the vertical axis is the number of scores, and it just about all fits. With the part you can't read, let me just pull down for a second. So the mean was 55.5, okay, out of 70. So what's that? You know, 5/7. Huh? No, that's 55. Mean 55. Oh, out of 75. Yes, out of 75. So I'll let you do the math. 55.5 out of 75. That was the mean, and the distribution was that. I mean, I'd rather it was more of kind of a Gaussian, you know, bell-shaped, Gaussian shape, rather than, you know, this long tail. So if you're in the tail, study hard, okay? Okay. All right. Now, just a couple words of review, and then I have sort of a special topic we'll do today, which is sort of not on the exam, and not really the next thing, but it's sort of an interesting thing that I want to tell you about, but that doesn't fit on the exam. But this is not comprehensive. How to write this? Some of the topics for the exam. So first off, Schrodinger's equation. You know, the square well, and then the traveling waves. Right? You've got to be able to handle that stuff. You've got to be able to handle the qualitative aspects. Okay, what are those? By the qualitative aspects, I mean sort of the boundary conditions. What do they mean? Why are they there? The idea of bound and unbound particles. Because, okay, we've only solved fully, well, we solved the infinite square well fully. You had homework on it. I solved the not infinite square well, the finite well, but we didn't really do a lot of math with that. And then I solved the step, and I sort of sketched solving the barrier. But as you saw, I gave you a homework problem that had, you know, an infinite well here and finite there. There's lots of things I could give you. I could have a plane wave coming into this and reflecting, and I could ask you, set up the boundary conditions. You know, I probably wouldn't say set it up fully and solve it, because that's just a lot of algebra. But I could easily, you know, so some mixture, you know, of things like that. And you need not to be freaked out. I need, you know, I'm going to ask you to demonstrate that you know exactly what it is to have a traveling plane wave going to the left, going to the right. You know, what are the boundary conditions, et cetera, right? That you've got to be fluent in, all right? Not, you know, this isn't, not you know, and you should be able to do them, but, you know, my goal is not to see how fast you are with the gory algebra of solving everything to the last degree. But if I give you a simple enough problem, I will ask you to solve it to the last degree, right? What was the flux, right? What was the flux? Remember, it was proportional to psi squared k. And when I say Schrodinger equation here, I mean you got to be able to solve it, right? You got to know what it is. You got to know how to solve it. One thing I mentioned in class, and we didn't do a lot, but I am going to consider it important. All right. So the ratio of its importance to how much time I spent talking about it is high. Okay. Is the notion of eigenfunctions. Eigenfunctions and eigenvalues. Right? And what's important about eigenfunctions and eigenvalues? Is a plane wave an eigenfunction of x? Is a plane wave an eigenfunction of x? Yes? No? Show of hands for yes. Show of hands for no. Show of hands for you don't know. Okay, shame on you guys. Right? No. Shame on you guys. Okay. You got to be, that will be that sort of thing you got to know. Right? A plane wave, an eigenfunction was, if I have something like the energy, which I now say the energy operator was I h bar d by dt. If something is an eigenfunction of energy, if this full wave function is an eigenfunction of energy, it's some constant times the wave function. And a plane wave if you take a derivative with respect to x, you get k. If you take a derivative with omega, you get omega out. So this thing is an eigenfunction of energy, right? Because they all end up there. Because E hat, E hat on psi is I h bar d by dt of e to the I kx minus omega t is I h bar. The derivative is minus I omega, and then I get back psi again, right? Which is simply I times I is minus 1 minus plus it's h bar omega, which is the energy times psi. Sorry, it's h bar omega times psi, which is the energy times psi. Where here I distinguish E as just a number and E hat was the operator, right? So a plane wave, and so once again, did a plane wave, does it have one value of momentum or one value of position? You do know that, right? Does a plane wave have one value of position? No, it's a function of x, and it's just the same well, it's oscillating, but the probability, which is to square it with complex conjugate, is just constant everywhere. So it's not one place in x. So it's absolutely, it is as far from an eigenfunction of x as you could get. All right? Even though if I write x hat times psi That is just x, the function, the variable x times psi. But that's not a constant times psi. That's different. Even though it's not a derivative, it's not, this is complicated. If I want to do an integral, that's inside the integral. All right, so a plane wave is an eigenfunction of momentum and energy. All right? Therefore, it has no well-defined time and it has no well-defined position. And we talked a lot about that sort of thing. And so that's maybe a second, well, so you need to understand this sort of thing. Although I didn't talk a lot about eigenfunctions and eigenvalues, I want you to understand the notion of a state that is either, in a defined position or a defined momentum or whatever it is. And then I do want you to learn this language that it's an eigenfunction and the eigenvalue. The eigenvalue here is E, is h bar omega. Okay, it's the value of the operator acting on the thing. Because remember, what is, in this case, what is the average energy? The right way to talk about it, the full way to talk about it that's exact, is I do that. I construct this thing. I integrate over all space and in principle all time, although we didn't really talk about the time integral, so I'm just not going to make you responsible for that. I integrate over all space of the operator sandwiched between psi star and psi, right? So P average, and we call this the expectation value. It's nothing other than the average. It's just, I don't know, I guess quantum mechanics is nice and fancy, so we better give it a fancier term than average. We call it the expectation value, okay? It's called the expectation value. Actually, I shouldn't be that cavalier. It's called that because it's just really highlighting this fact that you have psi, it gives you a probability, and all you can learn is the probability that something happens, and this is sort of what you expect on average. So we call it the expectation value, etc. And you see how eigenfunctions work. If p hat acting on psi is a constant, then the constant comes outside the integral. And what is the integral of psi star psi? Dx from minus infinity to infinity? It's 1, assuming we properly normalize psi, all right? Always, no matter how complicated the problem, that's equal to 1. Right, so and that's why eigenfunctions are useful, eigenvalues are useful. So I want you to have that concept in your head. Based, and based on what we've been talking about, right, there's the Heisenberg uncertainty principle. Delta P, delta X is greater than h bar over 2. And we spent a lot of time working on plane waves and showing how there was a packet, and the packet could either be broad in X or broad in P, but the probability, the product of the width in X and the width in P, Heisenberg showed that it has to be at least greater than h bar over 2, and it might be typically around h bar over 2. Remember I showed you that for the particle in a box lowest state. You actually calculated it, right? It was 0.6, 0.58, I think, h bar, right? So you got to have those concepts down. Going back a little bit earlier, there were the problems, not the problems, there's the, so let me see, this is maybe 3. There's also the delta T, delta E. Also, what is sigma? You need to know what that is, right? At a qualitative level, I want you to remember something about, just review the sort of the introductory part about photons as particles and matter as waves, right? Right, electron, so there's the chapter 3, which is kind of introduction to quantum mechanics. I clearly de-emphasized it a bit. I give you a few problems, let you read, but don't, I might put a thing or two in there to make sure you were paying attention. What was the photoelectric effect? Sorry, my handwriting gets really cruddy at the bottom of the board down there. So this was chapter 3, sort of the intro stuff. there's not going to be some hot and heavy problem where you're working all this stuff out and that's the centerpiece of the exam. But I might ask you a couple of things. Okay? Yeah. No, just that that's what it is. What its definition was, right? Because this term delta here is kind of vague. And with the mathematical statement of the Heisenberg uncertainty principle, you actually meant sigma. Okay? All right. Okay, so the topic for today, it's something I want to show you because it's an interesting and important thing. It's not going to be on the exam. It probably won't appear in any exam, but nonetheless, it's an important feature of actual particles. So far, when we worked with the full, and I'm going to ignore constants for the moment, the constant out front. This was the plane wave. And remember, so that's infinite in extent. And then remember the day when I used the computer and we worked and looked at packets, and of course then we spent some time on that. Implicit when we did that was we had k and omega independent, okay? When we sort of worked through a lot of that stuff. But k and omega are not in general independent. If I have a particle, the energy is h bar omega, where omega is this weird quantum mechanical phase term, and it's this term, right? Which when you take the probability, it goes away. But nonetheless, it's there. There is an omega. It's this oscillatory term of the wave function that just is there, okay? But it's also like this is a free particle. In other words, u equals 0. The plane wave. This is also equal to p squared over 2m equals h bar squared k squared over 2m. So omega is just h bar k squared over 2m. So omega and k are not independent. And that actually makes things a little more complicated when I do this whole packet analysis. Okay? When I do the packet analysis, things are a little more complicated. And so today we're going to explore that. And we're also going to explore a little bit what, this omega, which in many situations does not have a physical meaning. What is the effect of it? Having written this down for a free particle, remember for a photon, and this you should be able to do for the exam, what was this result from relativity? How are energy and momentum related for a photon? You need to remember this. If I forget, I always go back to p squared equals p squared c squared plus m squared c fourth. It's one of the most important formulas from special relativity. If m is 0, E was P0. E equals PC. Right? And that's the right way to think about a photon. So for a photon, E equals h bar omega was P times C, which is h bar k C. So omega equals kc. Okay? So even for a photon, omega and k, in fact, are just directly related. And maybe this got lost in all the stuff you've had thrown at you this semester, but notice again that for a particle, this h bar omega, the omega here, is kind of this weird quantum phase. This quantum, it's this omega t, it's this oscillation in the wave function. In most respects, it has no physical meaning. It almost always just disappears when you look at a probability. For the photon, if I write down the wave function, it's also true that it disappears when I look at the probability. But remember, for a photon, omega turned out to be the real honest-to-God frequency of the light. Okay, so there's this kind of difference between the photon and the particle in that respect. Okay. Well, so on to the point. Remember that I first constructed a packet by adding just 3 frequencies together of plane waves. I added one frequency, I took a frequency, and then I added 2 nearby frequencies, each with half amplitude. Do you remember that I did it in the computer? Let's take even a simpler case, because I'm going to do this just mathematically. I'm going to do this on the board instead of on the computer. Let's add 2 waves around K0 and omega 0. And by that, what I mean is, I'm going to say I have one wave with K equals K0 plus dk, and K is K0 minus dk, where dk is some just small difference from some basic wavelength, some basic wave number. And omega is going to be omega naught. Let me just write it this way. Plus or minus d omega. In fact, let me write this that way. Apologies for changing notation. But K0 plus or minus dk, and omega 0 plus or minus d omega. All right? So psi of x and t, and I'm going to suppress a constant here, whatever factor is out front. It's e to the I K0 plus dk x minus I omega 0 plus d omega t plus e to the I K0 minus dk x minus I omega 0 minus d omega times t. That's what it is. I wrote it out. Okay. I K0x, I omega 0 t is common to these guys. So I can write this as e to the I K0x minus omega 0 t. Right? I can take, I can separate this thing into e to the I K0x minus e to the I omega naught t plus in the numerator these terms, and then I can take these terms out as a prefactor of e to the I dk from this term, x, but then I have, e to the I dk minus d omega, I'm writing that wrong badly. This is that term, then I write this term, dk x. This is that term, and then I have this term, minus d omega t plus e to the minus. I already accounted for that term, but now I have that term, e to the minus I dk x minus a minus, there's a minus there, d omega t. Straightforward algebra, that's all I've done. Now remember, if Euler's theorem says e to the I theta is cos theta plus I sine theta, then e to the minus I theta is cos of minus theta is just cos of theta, right? Cos of minus x is cos of x. Plus I sine of minus theta is minus sine theta. So just by the definition of what happens when you do a cosine of a negative thing or sine of a negative thing. If I sum these, then I have 2 cosine theta equals e to the I theta plus e to the minus I theta. Maybe you just remember that. I always remember just this, and I just rederive. So isn't this? This whole business is just 2 cosine dk x minus d omega t. And then I have a prefactor. Let me move the 2 over. Right? That's all that it is. This is very straightforward algebra. It's just a little bit tedious to write it all out. But what did I learn? Something interesting. Remember what we said at the beginning, and this you need to remember. A wave actually, I mean, it's a sine or a cosine, but a wave that travels is any function of the form kx minus omega t, where these are the constants and they have the, in general, whatever that value number is, I interpret it as 2 pi over the wavelength, and whatever this is, I interpret it as 2 pi over the period. Just for sinusoids. But even if it's not a sinusoid, this moves with a velocity equals omega over k. That's what this does. So this is what I kind of started with. This is my normal plane wave behavior. I said I wanted to add 2 waves that were centered around k0 and omega 0. By centered around, I simply meant, basically they're k0 and omega 0, but a little bit different. And what I find is then I'm getting something that I've got my e to the I k0 x minus omega naught t wave. Here I've drawn it, say, in x, or I could draw it in time. But I'm multiplying it by cosine, which is similar to exponential, something that has dk and d omega. And dk is much less than, or is less than k. So presumably, I mean a lot less than k, but mathematically I'm just saying it's less than k. All right? If dk is less than k, this is 2 pi over d lambda less than 2 pi over lambda, which is to say, when you flip this, you reverse the order of the inequality. So d lambda is bigger than lambda. Okay? I meant I was adding waves that had, well, d lambda is bigger than lambda. So basically, if this is an x, I have some overall large modulation. And I'm multiplying this times that, right? I am multiplying this times that. So my overall wave looked like, well, I've drawn that. Now if I pretend I multiplied them, I'll draw the overall amplitude first. This is the cosine dk x. Let's just consider, consider the x part, the time, forget the time part. Then this is an envelope which multiplies e to the I k0x. Okay, this much you've done before, right? We've done this sort of thing. Here's the key point. Here's the key point. This envelope has a velocity, and we call this the group velocity. It is whenever I have this form, velocity is the prefactor of t divided by the prefactor of k. So it's d omega over dk. Whereas this inner oscillation has what we call the phase velocity, omega over k. So is that clear? This is it. I'm going to do something next, which is even a little bit algebraically more complicated, but this is the main thing I wanted to show you. If I add two waves, I get this packet-like behavior, which I showed you almost the first day we talked about quantum mechanics. But the thing I had not talked about before is that, just anyone's? Is that there's a velocity associated with the original plane wave, e to the ik0x minus omega naught t, and it's different than the velocity associated with the envelope. Okay? So it's kind of a complicated thing, but you can imagine, in fact, you don't know, these are different velocities and you don't know which one is bigger or smaller. Okay? In fact, well, you don't know which one is bigger or smaller. Secondly, if I look at p of x and t, all right, for this thing, it's this times this complex conjugate, right? This thing will go away. It's 4 cosine squared dkx minus d omega t. This is not constant equals 1 or equals a squared. This is not the thing that was really unpalatable about trying to say a particle is represented by the plane wave, which is that when I looked at its probability, I just got a constant everywhere. This is actually a thing. It's still a little unpalatable because I just combined two frequencies. It's still this thing that has many, many humps. But that thing, when I square it, the interior part has gone away, this faster wiggle. All right? And I'm left with this envelope thing, cosine squared dkx minus d omega t. And that thing moves, and it moves with what we call the group velocity. This is the velocity of an actual particle. This is a fictitious It's the phase velocity. This thing can actually be greater than c. Okay? I can construct a system where this thing can be larger than the speed of light. But it's really just a quantum artifact. It doesn't convey information. It will always go away in the probability. It's always going to appear in a term like that. And this contains the real particle. Okay? In this case, since I've added two plane waves, I basically have a whole lump of particles, an infinite set of humps. Okay? But nonetheless, there's really a velocity associated with them, and the thing moves around. Okay, so it's a distinction between a group velocity and a phase velocity. All right? And even returning to this example here, I introduced this by saying k is some basic value plus a small increment. At the same time, omega is a basic value plus or minus a small increment. When I have an actual formula that relates omega and k, then I can actually calculate how dk and d omega are related. And so let me just make a small table here once again. If I have a free particle, omega was equal to h bar k squared over 2m. If I had a photon, omega equals kc. So the phase velocity, which is equal to omega over k, in this case is h bar k over 2m. In this case, it's c. The group velocity which is d omega divided by dk, which is to really take the derivative. If I take the derivative here, can't you see that I just get h bar k over m? Because the derivative of k squared is just 2k dk. All right? And if I take the derivative here, I get c again. So for a photon, the phase velocity and the group velocity are both just the speed of light. But for a particle, the phase velocity turns out to be half of the group velocity. So actually what would happen on this wave, where I see the two components, is the inside will go racing along at twice the speed that the envelope goes moving along. And the group velocity is the real particle velocity. This, you know, when I first learned this topic, the professor was rattling on and on about it. And I was just like, could not get interested. And I know this is a little bit dry and mathematical, but it turns out that as you go on in physics, this comes back and it comes back and it comes back. I wanted to introduce it. I wanted you to realize that there's two velocities. One is really associated with a particle. One is really just a quantum artifact. There is one final thing that people will do. If I write on the vertical axis energy equals h bar omega, okay, and I write on the horizontal axis k, which is of course 2 pi over the wavelength of the particle. For the particles, this is a parabola. This is a particle. And for the photon, it's a line. And in lots of interesting quantum mechanical systems, I'll get a curve which is neither of these. For the particle, the steepness of the derivative, right? The derivative is the group velocity. So here's something interesting. Depending on which value of k I pick, my group velocity is changing. Well, no, I mean, sorry, it changes, but no, that wasn't my point. It's just that the slope is the group velocity. The phase velocity is a line from that point to the origin. If you think about it, this is omega over k is that line, whereas d omega dk is the slope. Right? So that's the group velocity and that's the phase velocity. And you see this slope is less than that slope, which is just a factor of 2 between them. Okay? Whereas for the photon, it's the same thing. And you can even have particles that do all sorts of wacky things. Okay, solid state systems, there's collective there's fictitious, if you will, particles which result from the motion of a bunch of atoms in a solid. And they can have a curve which has like inflection and whatnot. And so you can have, you can have all sorts of wacky behavior. And this in general is called a dispersion relationship. Okay? The dispersion relationship is the relationship between omega and k. And it determines the group velocity, i.e. the real physical velocity of the particle. Now, why is it called the dispersion relationship? I have completely run out of time. And so I'm just going to kind of quote the result here, and then I have a quick movie. What I wanted to do for you, remember, in this whole theme I've been trying to develop about a plane wave being everywhere, a packet being constructed of various values of k, I said if psi of x, earlier, remember we did this? We constructed a psi of x which was a Gaussian envelope on a plane wave. We did this, remember that? And I showed you that A of k was, I quoted the Fourier Theorem that A of k can be found from psi of x that way. And if omega if omega is a constant, we found that A of k was also Gaussian. In other words, if I looked at this integral and threw away this term, just thought about the x part, and I use this to find the envelope function in k that gives me this wave, this Gaussian envelope just multiplying this plane wave, I got that value for the envelope A of k in k. And incidentally, right, remember now this is a nice thing for the exam, what is A of k? In some sense it's the wave function for in k, which in k is momentum just by p equals h bar k. So if I ask you the probability of a momentum occurring, I square A times A, I square A of k, right? And then that's the, and I have to stick in an h bar, but okay. However, now if I try to rethink this problem with omega in there, if omega depends on k, when I try to do this integral, I've got to stick in minus omega of k of t dx. All right? And, oh, sorry. That's one thing. I need to say one more thing. This is all true. But I want to think a little differently. Suppose I am given that envelope function in k. I do know that psi of x was going to be written this way. All of this, again, when omega and k weren't related. If omega and k are related, I have the Fourier theorem that well, I have that psi of x is the inverse Fourier transform. If you give me A of k, I have that. Okay? And then afterwards, and that's just psi of x, then afterwards, psi of x in t is psi of x times the phi of t. Right? And here just it's e to the minus I h bar omega t. No, it's e to the I omega t, which is energy over h bar. Okay. So all this is true, but it's also true that if you give me A of k, I can construct psi of x. If I throw away the omega t piece, I can start with this, use this formula, and derive that with this being psi of x. Similarly, I could start with this, use this formula, and I could find that. If I throw away the omega of t piece, the omega piece. But when I don't, but in a real system, I just showed that omega and k are related. Okay? So I really should have taken the Fourier transform of that, where I said I really need to consider the t piece. Okay? And so I've run out of time. I'll skip the algebra. But if I have omega of k with some function, it could be h bar k squared over 2m, I can do a Taylor series expansion okay? I do a Taylor series expansion. I generalize this by saying I need to stick in omega has a k piece. This will no longer be so simple, and it's not. And I plug this into here, and I just drop the higher terms. Notice that is what I called the phase velocity, etc. This is just a whole new term, the second derivative of omega with respect to k squared. I plug these in. It's actually in the book. I've run out of time. I had it prepared. What I'll find if I look at p of x and t equals psi of x and t squared is at the end of the day, I start with this. No, sorry, I start with this value. I started with a Gaussian packet in A. I use this and I use these things. I call this term D, and I call that V phase. It's the constant that I had here. Times 1 over Okay, it's quite a mess. Well, maybe not quite a mess. Actually, it's a bit of algebra, but it's understandable. The constant out front has a term which grows with time. So if I have a packet, if this is a packet, it's falling. The amplitude is falling with time. The integral is preserved. The area under this packet is the same. The particle doesn't change. You don't lose probability. It has a velocity term, x minus v phase t. So it's just moving. And the width here, sigma sub x, multiplies this term, which starts out being 1 when t equals 0. But then it grows. It's the same term that's here. This term and this term. So basically, what it says, I realize you may have to go. I'm going to show you a movie of what happens. If you need to leave, go ahead. I won't be offended. I ran out of time. I'm sorry. But this is a kind of a neat movie. Why isn't it? It is showing up there. Hold on, wait a minute. I think I got it. Forget it. I lost it. So what happens though, let me just say in words what the movie was going to show. This mathematical form here, as I said, get out of the way. This thing is moving and the width is broad, is getting bigger and the amplitude gets smaller. So what it is this is our best description of a particle. Remember this Gaussian envelope in K, which gave me a Gaussian envelope in X when I ignored the omega and the relationship between K and omega. When I include the relationship between K and omega, this is the best possible quantum mechanical description of a particle. And there's something very, very fundamental. As it moves along, the packet broadens and its amplitude drops. In other words, in quantum mechanics, if you create a nice, well-formed, best possible Gaussian packet to describe a particle, as time goes forward, unless this d term is 0, if this d term is 0, this doesn't happen. But if the d term is not 0, the particle gets broader and spread out. And d term is not 0, it's just the second derivative. When omega equals k squared h bar over 2m for a particle, The d omega decay is h bar k over 2m. D squared omega decay is h bar over m. It's not 0. So for an electron in quantum mechanics, as it moves along, you lose, you can make it confined, but then as it moves, it spreads out. The amplitude drops, it spreads out, and it becomes deconfined. Just that happens, okay? A photon, which had omega equals k c, right, h bar kc, the second derivative is 0. It doesn't do that. So a photon moves without spreading out. This process is called dispersion. That's why the relationship between omega and k is called the dispersion relation. The particle fuzzes out, it's called dispersion. There's an exact analog in optics, but it's not quite as mysterious or unusual in that no matter what I do with a real particle, as it moves, it just simply spreads out, okay? So I'll leave you with that, and see you tomorrow if you come, and Friday for the exam.